Ladies and gentlemen, we are team 1106, consisting of me, Nguyễn, Hồng, Minh, and my friends.
Nguyễn, Quang,
We all come from Ho Chi Minh City University of Science, and now we are so excited to present our solution for Robert A. It is raining space dust. In this presentation, we will get a glimpse of the cosmic dust. The assumption have been made. After that, we are going to expose the model we found to predict what will happen to dust when they enter the Earth's atmosphere, with and without stochastic factors that affect its orbit, as well as using size of a particle found on the Earth's surface at a certain time, and work backwards to estimate the distribution of its initial size, velocity, and angle when it just entered the Earth. Last but not least, we will have a tiny discussion about our model. Firstly, have a quick look at a brief overview of cosmic dust. It consists of tiny solid particles ranging from a few molecules to over 0.1 millimeter. It is the fundamental material for stars and planets. Therefore, scientists are eager to study it. Our project has two primary goals: simulate a particle's atmospheric entry trajectory and challenges based on its initial radius, velocity, and angle, using the observed size of cosmic dust on Earth's surface to estimate its initial radius, velocity, and angle distribution as it just entered the atmosphere. This complex problem solvable, we establish several key assumptions. The most important are the dust particle and the Earth are a perfect sphere, with no collisions between particles. The particle has perfect heat absorption and radiation with emissivity coefficient of 1, and our simulation begins at an altitude of 190 km. The particles are mainly made of iron sulfide, with density is 3 grams per centimeter cube. Average molecular weight is 45 grams per mole. Heat of vaporization 300,000 joules per mole. Mathematical limit of vapor pressure at infinite temperature is 3.98 billion pascal. Our noise-free model is built on a 2D coordinate system. In the OX-Y coordinate system, it is assumed that the dust particle begins atmospheric entry at coordinate 0, radius Earth plus 190, and is flying diagonally to the right. Positive is direction at an angle theta, so V is equal V sin theta, Vy equals minus V cosine theta. The minus sign in front of the cosine term for the Vy indicates the particle is flying downwards in the negative Y direction. So, how fast is the particle moving when it hits the atmosphere? We use a law of conservation of energy. We can send to the quantities and their units in the table. The kinetic and gravitational potential energy at infinity must equal the kinetic and gravitational potential energy at our 190 km starting point. By solving this equation, we get our first key formula. This gives us the particle's velocity in 190 km. Next, the change in momentum equals the sum of forces. We consider two primary forces, gravity and air drag. The drag force is proportional to the atmospheric density, the particle's cross-sectional area, and the velocity squared. The gravity is proportional to the acceleration due to gravity and the mass of the particle. This is units of quantities that the drag force depends on. To get the change of velocity, we divide this force by the particle's mass. After simplifying, we arrive at this fundamental equation of motion. Finally, we decompose the acceleration into its x and y components. We can see its components ax and ay is the sum of the air drag and the gravitational pull in that direction. To calculate bx, we just need to multiply v squared by sine, while by is multiplying v squared by minus cosine. Now, to determine the exact two components of acceleration, we also need to find gx, gy. When the particle is at the position shown in the figure, we have the formula for gravitational force acting on the particle, in which r orbit hat is a unit vector from the origin to the particle. We also know that gravitational acceleration g is gravitational force Fg divided by particle mass. We need to distinguish the notation r and orbit, with orbit is distance from the particle to the center of Earth, and r is radius of this particle. So, we have the final formula for vector g. This gives the full component for A. Its particle has coordinates x, y. Therefore, the distance from the particle to the Earth's surface is square root of x squared plus y squared minus the Earth's radius. According to basic physics, the change of position vector is velocity.
As the particle decelerates, the kinetic energy becomes heat. The heat input rate is the work or energy per unit time. In our model, P-ATM, SV is the mass of air that the particle collides with per second. Hence, P-in is half of P-ATM times S times V cubed. Simultaneously, the particle cools by radiating heat. This power output is governed by the Stefan-Boltzmann law. Because we assume the particles are radiative equilibrium, by setting P-in equal to P-out, we can solve for the particle's temperature, T. By plugging P into the formula of T, we get the reduced formula of T shown in the bottom. Next, let's turn to the equation of vapor pressure at a certain temperature. The vapor pressure is proportional to the exponential of minus heat of vaporization on ideal gas constant times absolute temperature. Once the particle gets hot enough, it's vaporized. The Hertz-Nielsen equation describes the rate of evaporation of a particle per unit area per unit time from a surface into a perfect vacuum. J is equal to the vapor pressure times square root of molar mass on 2 pi times ideal gas constant times T. Multiplied by the area of the particle, we have the mass loss rate. Because we assume the particle is perfectly sphere, so the mass equals 4 times particle density times pi times radius cubed divided by 3. From mass loss rate formula, change to variable r, we have the change of radius as shown. To summarize all the equations we just mentioned, let's look at the general diagram. Here is the full system with two initial conditions on entry velocity vector and position vector.
However, the real world is noisy. The actual forces affecting dust are far more complex, involving convection and weather phenomena, which are stronger in the lower, denser atmospheric layers. Therefore, we will model the magnitude of this disturbance force as a fraction of the red force. This is a valid assumption because the red force is also directly proportional to atmospheric density. This changes our deterministic model into a stochastic one. The change in momentum is now a stochastic differential equation, which has two parts, a return A, which is our original noise-free equation, and a diffusion term B, which has a random component. We assume B equals a scale factor of k times the drag force vector. We also consider the change of velocity in a stochastic model as well. It has two parts, return μv, which is our original noise-free equation, different term sigma v, and a random component. Now we determine them. Then we apply a multidimensional Ethers formula for a change of variables to rewrite the change in momentum into formula based on Vt and G. Because of the stochastic momentum change equation mentioned before, Bt equals Jacobian matrix times the diffusion term of velocity. Therefore, we need to know the inverse of the Jacobian matrix of G. It's simple. G is a vector, M is a number, so G is also a vector. To determine the inverse of the Jacobian matrix of G, first we determine the Jacobian matrix of G, its determinant, then its adjusted matrix. Combine them all, we have the diffusion term of velocity. This is the full system of noise model with two initial conditions.
To solve the whole system, we also need the value of atmospheric density at each altitude, and we will find the density at any altitude using simple linear interpolation. After solving the whole system, we plot four features for altitude, velocity, radius, and temperature versus time. In case of a small, low-velocity particle, in short term, at the 9th second, it reached an altitude of 120 kilometers and experienced a maximum temperature exceeding 900 Kelvin. However, this temperature does not exceed the material melting point. The particle does not experience any mass loss. In long term, this particle continues to descend. In case of the same particle but with high velocity, it plunges straight down. After 5 seconds, the particle reaches an altitude of approximately 128 kilometers and is heated to a temperature approaching 1200 Kelvin. This causes a particle to lose significant mass, reducing its size to only about 0.3 micrometers. In long term, this particle continues to fall slowly. Next, in the case of a large particle with medium velocity and a fairly wide angle, it's rapidly heated to a temperature of 1300 Kelvin after only 6 seconds. This causes the particle to lose mass quickly and vaporize completely. In the case of that same particle but with a narrow angle, it reaches a maximum temperature of nearly 1200 Kelvin. This causes the particle to experience partial but not complete mass loss, reducing its size to reach 8 micrometers. In long term, this particle continues to fall.
To run our simulations, we first need to generate realistic starting particles. We must sample them from known astrophysical distribution for velocity, radius, and entry angle. For velocity, we use probability density function from the paper Heating and Thermal Transformation of Micrometeoroids Entering the Earth's Atmosphere. Then we deduce its cumulative distribution function. Applying a method called inverse transform sampling, we generate a uniform random number u between 0 and 1, plug it into the inverse function v0, and this gives us an initial velocity. For initial radius, we reference a formula for cumulative particle flux, which is based on mass. First, we take its negative derivative to get a differential flux by mass. Second, we perform a change of variables, convert this function from mass to our desired variable radius. Finally, we normalize this function by integrating it over our range of interest from 5 to 1000 micrometer to create a proper PDF that we can sample from. For entry angles, we also reference the formula, which is the difference of sine square of two bounds. By choosing the theta 2 equal theta and theta 1 equal 0, we have the C shape. Then, using a random number u, we get our assembly formula is theta equal arcsine of root square of u. Shows the immediate entry phase. After just 1 minute, 43 particles have completely vaporized. None have hit the ground yet. Not a simulation, but in 1 day, because of a long time period, most of the particles hit the ground, 765 particles.
Now we return to our second and most important goal, working backwards. The problem stated is scientists have collected dust particles and measured their observed size. How can we estimate the initial distributions of size, velocity, and entry angle at the moment they first enter the atmosphere? The first idea we think of is to use Bayes' theorem, but you can see that the likelihood function, the probability of getting a final radius given a starting state is far too complicated to solve. We use ABC approach, which stands for approximate Bayesian computation. We will sample 1000 particles from the prior distributions. Each sample is defined by the initial parameters. For each sample, we run 1000 simulations based on our noise model. Using the Monte Carlo method, the expected final size of the ith particle is estimated by the average of its simulation results. We just accept the parameter sample if its expected final size is within the tolerance of the observed data. We choose tolerance is 10% of the observed radius. In the case of the observed size of particle found on the ground is 5 micrometers. The most probable initial radius is also 5 micrometers, which means the particle experiences no mass loss. The most probable initial velocity is the lowest one, 11.2 km per second, while the entry angle is around 45 degrees. If it's 20 micrometers, the most probable initial radius is approximate 20.5 micrometers. The velocity is also the lowest one. The most probable entry angle is bigger, around 70 degrees, which means large particles need a narrow entry angle if aiming to survive. Let's discuss about the strength and weakness of our model. Our model is only applicable to perfectly spherical particles. Thank you
for listening.